Okay, how did milestone 2 go? It's done? Was milestone 2 fun?
A bit more time, extra week, you know.
An extra week would be good? Okay, so a little bit stressful, I guess, at the end. Mostly fun, some stress, some fun. Okay, I'm gonna take that as mostly. Okay, so we're gonna start talking about milestone 3, which is due in a little less than 3 weeks. Okay, so you got some time, but we're gonna start going through what you need to do it. Okay, so milestone 3 is partly going to build on top of milestone 2. It is a user interface portion, but it also has an algorithmic portion. So you're going to find the shortest path between 2 intersections. So you're trying to find good driving routes. It's worth 15% of your final mark. So 6% of it's going to be the algorithm. And that'll be auto-marked, so you'll be able to see how you're doing on the public versions of the tests. So you have to find a connected path that you could legally drive between 2 intersections. You'll get a few marks for some path, but you'll get more if you find the shortest path. So a bunch of our tests, some of our tests just check, did you find any path? It's legal. Other ones check, is this the best path or very close to the best path that you could get between these 2 intersections in terms of how long it takes to go there. And then some other tests basically are increasingly difficult in terms of CPU time. So they're going to check how efficient is your algorithm. And some of them are not very hard to pass, and some of them get a bit harder to pass. 7% of your mark will be user interface. So you'll build on top of what you did for M2. But you want users to now be able to enter in various ways. I want to go from A to B, and you want to give them good directions, visualize how they should travel this route. And then 2%, just like in the last milestone, is going to be on how you did this, code style, project management. Part of project management, put on the rubric, is going to be don't get everything done at the last minute. So set milestones, track who's doing what, and also get some of it going earlier so you can actually iterate, so you're actually showing agile development. Okay, it's due on March 30th. Okay, so you need to find a driving path. So we need to give you the spec of what is the travel time of a path. It's basically, we're going to be very optimistic about how fast you can drive in a city. You can drive the speed limit. So the first part of your travel time between 2 points is just how far did you go on some street segment divided by its speed limit. Okay, so let's say I'm going from here, near campus, to here, McCall and College, another spot near campus. So I need to travel 200 meters north, 300 meters to the east. So I can work out what street segments I should take. I can work out their speed limits and how long each of them is. And that's going to be part of my travel time. Now, it's not the only path. I could also, instead of starting out at this corner of Cecil and Ross and going north, I could instead go east. And then I could turn left and then go along College for a while. So those are 2 different paths that I could take. And our travel time is not just kind of distance travel divided by speed. We're also assuming that whenever you have to turn, and or kind of go through, change streets, basically. We basically say if you change streets, that involves a turn or going through a traffic light, it's going to take you some time. So let's say that time we assume is 15 seconds. We'll call that the turn penalty. Then if we take this blue path, well, we've got 300 meters, and that's on College, relatively major street. Let's say its speed limit is 50 kilometers an hour. We've got 200 meters that we went north on a smaller street. Let's say its speed limit is 40 kilometers an hour. And then we turned once. We turned right there. So if we add all that up, we get 54.6 seconds. For the red path, the distance is actually the same. But we go a little, this is a slower street. So we go 100 meters on a slow street, divided by 40 kilometers an hour. We go 200 meters on a slow street, divided by 40 kilometers an hour. And then we'll say College is 50 kilometers an hour, so 200 meters along it. But we turned twice. Okay, we turned there and we turned there. So we had 2 turn penalties, and we get a travel time of 71 seconds. So both of these paths are legal, right? You could drive them, but the blue path is superior. It has a lower travel time according to the metric of travel time we've given you, so you'd want to return this blue path. Okay, hopefully everybody's with me. So that's your specification of travel time. To make sure you've got that specification of travel time right, we have unit tests for this milestone. And the simplest unit test is one that just you give it a travel path, or it gives you a travel path, and you return the travel time. So that's going to check that you understand this spec. It's not very hard to write, but it's like the first function you should get going for this milestone. Okay, so that's the definition of travel time. You have to write a user interface, and that's worth 7% of your final mark. It has some requirements. The user has to be able to enter 2 intersections, and you can find the path in between them. So, and those 2 intersections, they should be able to enter, it's similar to what you did for milestone 2, so you can build on top of that. They enter the names of 2 streets, you figure out where they intersect, and they're gonna have to do that twice, so that you can get 2 intersections. That's not the only way they can enter intersections. They should also be able to just click on an intersection, and you might choose to make it possible for them to mix and match this. So that's how they enter, what am I trying to do? Once your algorithm has found a travel path, you want to be able to visualize it in the user interface, so draw it somehow. You want to give them travel directions, so to just draw the path, make some text or some icons that explain how you should follow this. And we want your user interface to be essentially self-documenting. Your TA should be able to figure it out without you there, which means you should have a help button or some tool tips, some way that explains how to use this user interface and what it's doing. Okay, so that's all your required features for the user interface. And we have a rubric to give you a little more guidance on how to do this. We don't just want you to meet those basic requirements, we also want you to try to make it highly usable. Good ways to test that are test it on people who aren't the development team. So try it out on a friend or family member. Can that person enter these intersections and click on these intersections without a lot of pain? Can he or she follow the path directions and the path display, or do they get confused? Do they need a lot of guidance where they're asking you questions, because your ideal is you just give them the user interface and they just figure it all out. So test that on somebody who's not on the development team. Okay, so this travel directions, you can actually make more or less usable. So let me show you the initial one that Professor Chong and I came up with. Okay, and I took the lead on making these travel directions. So I get the path and I say take street segment number 21, then take street segment number 10, and so on. So what do you think? What do you think of my travel directions? What do you think your TA would give you for this? So this is unimaginably bad. Okay, this is kind of directly printing out what your algorithm is going to return. Your algorithm is actually going to give you a vector of street segments. That's going to be your solution. Showing that to the end user is really bad. Obviously, they don't know what any of these IDs are. I should never see something like this. Unless maybe I have a debug mode, right? You might want to see this, so that's fine. Maybe you have a debug button or a debug option, but should never show this to a regular user. Okay, so Professor Chong pointed out this is not the best, so we made it a bit better. So again, our solution that comes back from our algorithm is this vector of street segments. So we're gonna be a little smarter. We're gonna go get the name of the street that each of these street segments is part of. We've got a little bit of code for that. And we could say take Yonge Street, then Bloor Street. What do you think of these directions? Seem probably better, but can you immediately see any problem with what I just did? Even from these 3 lines. So A09, so let's go to you. What do you think?
When it says take Yonge Street, then Yonge Street, it doesn't really specify
Yeah, this looks a bit bizarre, right? Take Yonge Street, then Yonge Street. I guarantee there will be quite a few teams that their travel directions look like this. The reason is exactly why Professor Chong and I made them this way. Our actual solution from our algorithm, you're going to see in a few minutes, is a vector of street segments. So if I just write a little bit of code to figure out what's the name of the street, and I print that out for every single street segment, this is what I would get. But it's pretty user hostile. If I drive along Yonge Street for 20 blocks, I'm going to say, take Yonge Street, take Yonge Street, take Yonge Street, take Yonge Street. Like, it looks like my navigation assistant is like a little bit passive aggressive, right? Like it's kind of annoying. So don't do that. And it sounds, you go, well, who would do that? Lots of people will do that. So, and this is, to try to find those blind spots is where it's actually quite useful to show your UI to somebody that is not in the team, because they'll immediately say, oh, this is kind of bizarre. The reason people don't see it sometimes when they're coding it is it seems natural when you know what data is going in. You're just doing a conversion on the data. Okay, so we're going to check, do the directions give you the information you need to go from the start to the finish, and they're pretty easy to follow. Okay, so I'm going to put up the timer. So in your team, or if some of your team are not here, go join somebody else. Just work out for the next minute, what are all the things you think you should put in these travel directions? How would you attack this? Okay, so let me show the timer here. Okay, then we'll discuss that as a group. Maybe I'll give you a couple minutes, because I think it's probably too short to ever do things for 1 minute. Okay, so I think we're going to call on some teams here. Somebody's got to have a good idea on this. So if you've got an idea of what you'd like to see, buzz in. And I think I owe a few people chocolate bars anyway. So if you participate, come up afterwards if you'd like a snack, okay? All right, so A09.
All right, so for travel directions, I mean, you've got yourself like arrows you can like have on the user interface. arrows drawn pointing left, right, straight,
Okay, wait, so you're gonna have arrows.
corresponding to the instruction.
Wait a sec, so arrows to show directions.
Yeah, show direction of like travel, like whether to turn left or to turn right or to continue ahead.
Okay, so directions of turns, you know, go straight, etc. Okay, so you're gonna tell, makes sense, turns are pretty important. Okay, so you're gonna show them all the turns. What, anything else?
Display the instruction itself.
Okay, so you're gonna display instructions. So what are you gonna put in the instructions besides arrows?
It's going to be like words basically telling the driver to either turn left or what basically turn they should be making into which
Okay, so you can tell them which turns, left, right.
Maybe like distance as well.
Okay, anything else?
and
Are you gonna say like make a left, then a right, then a left, then a right, then two lefts, then a right?
I mean, it would tell you also the street or the street that you're turning into.
Okay, so you need street names. Anything else?
You can also, I mean, as an extra, probably have like a voice tell you this.
Okay, so you can have a voice. You can make, actually a few teams did this for Milestone 2. You can use voice tools to actually make this talk if you want. That would be kind of a bonus. We don't expect you to do that, but if you go do that, that's cool. You could animate things. Some teams do that. Again, we don't expect that, but if you do that, that would be extra usable. Okay, so maybe put voice in. I'm gonna go take, anybody else? Okay, C07. I can see, let's see, where is C07? Okay, any ideas from C07?
Maybe distance traveled on the road till the next.
Right, so distance would be a good idea. So if you say, if I don't know where Steeles Avenue is, and you say drive on Yonge Street and then turn left on Steeles, I gotta kind of have, I'm gonna be tense, right? I've been driving for a long time, I still haven't seen Steeles, maybe I missed it, etc. So distance is a good idea. So distance along street. Any other ideas? Anything else you tell people? Okay, any thoughts? Okay, so A09, got another thing you'd put in?
Maybe like ahead of, maybe by 500 meters or something ahead of time, like you would remind the user like, hey, like turn right or something, so that they know like to switch lanes.
Okay, so you're saying tell them the distance and then turn right. Is that right?
Like to, I mean, well, it's more of a voice thing. Just like to make sure that you notify them when they're getting closer to that point.
Okay. Now we're not actually driving, so you're going to kind of give them the directions all at once, right? If you manage to like take the UG machines, strap them to your back, and run around with them, you get bonus marks from your TA. But that would be extra challenging. Let's see. Think about the user friendliness of this. So we'll often see solutions that say go 336.8889 meters along Yonge Street. And that looks a little intimidating, right? Like, wait a sec. I don't know if I know when I've gone 336.889 meters on Yonge Street. So, look at your directions and make sure, they don't look kind of silly. You're not overwhelming people with unnecessary detail. Any other things you'd put into this? So there are more things you could put in. Let's say you start out. Okay, so we start at a certain intersection, okay, and we're going to a certain intersection, and I say go on Yonge Street. Let's say I go on Bloor Street for 500 meters, then turn left, go on I don't know, Davisville for 200 meters, and then go on St. Clair for 600 meters, okay? So I could tell you all those things. Were those directions complete? So I said go 500 meters on Bloor, and then I said turn left, go 300 meters on Davisville, then go 700 meters on St. Clair. It's good? What do you think? Can you follow these directions? Does anybody see a flaw in my directions? Your TA will see a flaw in these directions. Okay, so I'm starting off here. Let's say this is, I don't know, Bloor and Spadina. So I might tell you, probably a good idea, start at go to, okay? So I can put the start and the destination in. It might be a smart thing to do. Is there anything else that's missing? Okay, so there is something that's missing here. Yeah, so A09. What do you think I missed?
The destination? I mean, you have the.
I didn't write that down here. So let's say this is St. Clair, and I rarely go east of Yonge. I don't know why. So let's see, what's St. Clair and Parliament? Let's say Parliament hits St. Clair. Okay, so I'll tell them the destination too. That might be good. Anything else that I'm missing? Yeah.
What's this line that you draw? Like you drew a slanted line, but
Well, that's just messy. That's Davisville.
What is the name? Maybe the names of the.
Yeah, so I should give these names. So I just got lazy. I didn't put them in.
Okay, there's still something.
Okay, so I should have all that stuff. But there's one other key thing that's missing that a fair number of people will miss. So it's your reward for attending, right? So D05. What else am I missing?
Like northeast, southwest?
Yeah, so I could tell them which direction. That's actually probably helpful in general, right? If I've got a compass or a sense of direction, it might tell me something. Where is that particularly useful? It's particularly useful at the start. Okay, so if I say start at Bloor and Spadina and go 400 meters or 500 meters on Bloor and then turn left on Davisville, I have a 50-50 chance of ever getting to Davisville based on if I don't know Toronto. Okay, because you didn't tell me which way to go. You told me to go on Bloor. I'm going to pick a direction at random. I might hit Davisville, or I might have to go all the way around the earth. Okay, so that's not good. You should definitely tell people what direction to go when they start. Yes, you disagree? You think you would get it?
No, but does that mean that we need like you know in GISs you've got like yourself represented graphically.
Yeah.
Do we need ourselves to be represented graphically for?
Well, you're giving travel directions where you say, you are here, you will get there. So you don't need to represent yourself graphically.
Because like when you said about if someone doesn't know Toronto, like for example, if I go to a city and don't know, I see where I am and where I'm looking at, and I just follow. I look at the map to get to the place.
So you're right that if you look at the visual display, you might be able to figure out, oh, I should go east.
Yeah.
Okay. But it would be better if my directions actually said start out going east, right? And if you draw it all the directions are integrated with a graphical display, then you could argue, well, the graphical display shows you which way to go.
Okay.
But it is still more convenient to tell them which way to start. Okay, so yeah, directions are also helpful.
Okay.
You could make this more fancy. You could say things like sharp left, gentle left, etc., all sorts of stuff. But this is kind of the basic things that you want to make sure you get in there. And yeah, look at it and make sure it's not doing things like giving the 333.68 meters that I talked about. Did you have another comment?
I mean, like, I guess you could tell the user, like, to look, like, which direction to look, and then say, like, in the direction of blank, turn, like, go straight. I don't know.
Yeah. So I think telling them compass directions plus turning could be good, but for definitely when you start off, you want to tell them which way to go, because otherwise they might just go the wrong way forever. Okay, so yeah, those are some ideas on how you make this. It's nicer if you try to integrate this into your UI. So this is on the rubric, but the most basic version of travel directions would print them to the console. It's going to be much nicer, more usable if it's integrated in your UI. And you're also going to want to visualize the path. So at the very least have the text and the path kind of near each other, but you might be able to integrate them more closely. Okay, so planning. So you should start early. Don't leave this to the last couple of days because it'll be really stressful. And you want to divide up the work. Milestone 3, much like milestone 2, is a bit too big for you to just have one person coding and 2 people navigating and giving feedback. So you got to divide it up more. So how can we separate this for parallel development? So let me give you a minute to talk among your team. So like I said, you have these components of a person. I told you about the user interface. There's also an algorithm. And the algorithm has to actually find the path between these two things, and we want it to be fast, CPU efficient. Okay, so given that amount of information, why don't you take a minute and just discuss with your teammates, how can we chop this up so that we can have independent pieces that we're working on? Because this is always a challenge in any project, and certainly in software projects. How do you chop it up to get parallel development going? So think about that right now. Okay, does anybody want to volunteer some ideas of how to split this up? So how can we get parallel development going? All right, C07, what do you think? How would you split this up?
I split it between the algorithm and the UI, mostly.
Okay, so you can definitely do the algorithm separately from the UI. Some students struggle with this, so it makes perfect sense. Okay, so algorithm, one person, UI, another person, so that's only two. The third person gets a break, but let's come back and see if we can split up some more. What we sometimes get questions from students, well, how can I split the UI from the algorithm? Like, how can I test one of these things? Now we have unit tests for the algorithm, so it's pretty obvious how you could test the algorithm, because we can hook right into your algorithm. That's good development. What about the UI? Can the person writing the UI test when there's no algorithm? So you're supposed to be displaying a path, giving travel directions, but you have no algorithm. So how can we unblock this? Because a naive way to do this would be to say, okay, well, I guess I can't test any of my path display code until after I've done the algorithm. But that's risky, right? I'm basically moving things now closer to the deadline. So what would you do about that? Okay, so we got the idea of algorithm and UI separate. It's a good idea. How can I test essentially the UI when I don't have an algorithm yet? And this isn't a really complicated question. So if you're going, oh, okay, so C07, what do you think?
Maybe create a fake set of data to put into your UI.
Yeah, so you can essentially, it's like stubbing out. In milestone 1, before we had functions written, we just stubbed them out. We just put in like an empty function, didn't do anything. So we can use this same kind of related idea to test our UI. We can just hard code a path. We can look at the street map data and just find a couple of street segments. We can write a little code to do this, find a couple of street segments that are connected and say, okay, that's our path, right? And maybe we'll find a few more, make a longer path, and we can just basically set up a vector that stores that, because that is how we encode our path. That's what our algorithm's going to return. Once we do that, the person writing the UI to display a path can just use that. Okay, so they're hooked up to one hard-coded path. After they've shown that one really well, maybe they make another hard-coded path, but you've broken a dependency. So yeah, it's the right way to do it. So I guess one thing, we can go a little further. We can break up the input UI is actually independent of the output UI. So we need to be able to, with both mouse input and text input, find two intersections. Well, you can write all that code and just basically return those two intersections, highlight them, print them out, whatever. You can confirm it works. You can make sure it works no matter what the person types, etc. So that can be done as one task. The output UI is a separate task, and as I said, and there's even a couple of pieces of it, giving directions, drawing the path, so you can even split this a little more. To make sure you can test it before the algorithm's working, just make a hard-coded path. And you might have to write a little bit of code to find that hard-coded path, or maybe you put a little code in your UI that when you click on an intersection, it tells you all the street segments attached to it. You can use that to now find a path, and you can hard-code that. And then you have your algorithm. And your algorithm can be divided up some too. So you can say, well, I want to get a basic path search going that just gets me maybe a legal solution. And I could split the coding of that from the testing of it, so that can get me a little more parallelism. I could also, with some more planning, have two team members collaborate on this where they work out what functions do we need, and they each write some of the different functions. But that takes closer planning. Once you have a basic path search going, you can try to make it faster. Okay, so we're going to teach you increasingly sophisticated path search algorithms. You could start off with one of the ones that is not terrible, but not the most sophisticated, and then add in features. So all these ideas are to try to stop you from getting into a challenging situation where you've kind of made everything depend on everything else, and you wind up doing too much work near the end. You want to get parallel development going early. Okay, and you write this down on your wiki, you tell your TA about it, your TA is impressed with your project management. Okay, so that's it about the UI and about how to kind of attack dividing this up. Now we need to start talking about algorithms. Okay, so we want to go, for example, from here to Canada's Wonderland, right? It's what I'm going to be doing right after the course ends. So how do I get there? We're going to model this as a graph problem. And you've already seen we're modeling cities as graphs. Nodes are intersections, street segments are edges, so you already know this. A path from between two intersections is a sequence of connected edges and nodes. Okay, so if I want to go from this source intersection to this destination intersection, I just need to find a path in between them. And again, a path is a term that's defined precisely in graphs. It's a connected sequence of nodes and edges that gets you from the source to the destination. Okay, so I just drew what a path looks like. We need to decide how we're going to store this in code. So we could store it as a sequence of nodes, like a vector of nodes. Okay, so every one of those circled intersections is a node in our graph. It has an ID. We could make a vector of those node IDs and say that's our path. It's not bad, but there is a shortfall in this. Can anybody see why this is maybe not the best way to do it? This isn't a ridiculous way to store a path, but in these street graphs, it's not the best way to store it. There are a few cases where this is problematic. So can you see any problem if we made this the output of our path search algorithm? Okay, I'll give you a hint. Let's say there's a back lane. Okay, so between those two nodes, there's the regular street, but there's also the back lane street. Now do you see any flaw in encoding the path as a sequence of nodes? Okay, so what is the flaw? There is a flaw. It doesn't give us as much information as we'd like. This sequence of nodes could represent a path that goes like this, or it could also represent a path that goes like that and takes the back lane. So it's ambiguous. So we'd rather not have an ambiguous representation. Now, most of the time, it probably won't be ambiguous, but sometimes it could be. Okay, so what we're going to do instead is we're actually going to store the sequence of edges. And in our case, edges are street segments, so we're going to have a vector of street segments. And that is always unique. Okay, even if I put that back lane in, if I don't take the back lane, then I have this sequence of edges. If I did take the back lane, I would get rid of that one, and I'd take this instead. So it's always a unique representation. So that is your output of the algorithm for milestone 3. Okay, now we need to make this algorithm. We need to find these paths or these routes. Between this source and this destination and this little bit of city, do you think there's only one path? Or do you think there are many paths? So what do you think? This is not a hard question. So how many people think there's one path? Okay, how many people think there are many paths? Yeah, so there are many, many paths. Okay? We're giving travel directions. We don't want to return any path. We'd like to return a good path. Okay, so what's a good path? I mean, it could be the fewest nodes, so the fewest intersections. It could be the fewest edges, so the fewest street segments. So, those paths, if I say those are my best paths, then both of those would get rid of, driving directions that go around in big circles like that. Okay, they wouldn't like that. But neither of them is the best definition, like the one that really matches what a driver would want. What do you think the best definition is of what's a good path? What should we check? Yeah, so A09.
The path that takes the least amount of time to...
Yeah, so what we're going to do for this one is the least travel time. And minimum travel time, and we've already told you how to compute that. So we have a certain amount of travel time on an edge. It's basically the length of the edge, the street segment divided by the speed limit. And then we also have this turn penalty, so a bit of an extra cost that we're putting in. What we're solving is a classic graph problem that's called the we're finding the minimum weight path between two nodes in a graph, or this is more commonly called the shortest path. But shortest is defined according to this, weight. And you can put weights on nodes, you can put weights on edges. We're putting the weights on edges. So you'll find this problem discussed in a bunch of graph textbooks. It actually turns out it's not only an important algorithm in its own right, it's the building block for all sorts of graph algorithms. So this is an important one to understand. Okay, so let's get precise about the travel time definition. It's the street segment length divided by the speed limit. You wrote a milestone 1 function that can return this. So for any street segment, you already have a function that returns the travel time of that street segment, and we speed tested it in milestone 1 because you want this to be really fast. So if you failed that speed test, talk to your TA, you really want to pass it. Because when you do these path searches, you're going to call this a lot. And then we've added in this turn penalty. Okay, so the turn penalty, to make it a bit easier to compute, we're not making you do a bunch of coordinate geometry to figure out am I turning left or right. We're just saying if the street ID changes, there's going to be a penalty. Okay, so if this is a little piece of my graph, I'm on Bloor Street West, that has a certain street ID. I've got Bloor Street East, that has a different street ID. And then Yonge Street, let me change my, see if I can change my color here. Let's say Yonge Street, actually, that's one street. Okay, so these two street segments are both part of Yonge Street. Okay, so if I go straight up Yonge Street, even though I've gone between two street segments, I didn't change streets, we therefore assume there's no traffic light, no turning, and there's no penalty. When I go from Bloor Street West to Yonge Street, I turned, there'll be a penalty. And when I actually go from Bloor Street West to Bloor Street East, my street ID changed, there'll be a penalty for that too. So assume it's like there's a traffic light, this is a big street change. So we're keeping like this turn penalty relatively simple. You change street IDs, when you go between two street segments, you add in this turn penalty. Yeah, ece9?
Yeah, so my question is the shortest time taken to get to a place necessarily correlate to the shortest distance take?
Okay, so the question is, does the shortest time between two intersections, does it correlate to the shortest distance? It will correlate some, but it's not exactly the same. If I'm on a freeway, even if I go a little bit outside of my way, it's probably faster than if I take a bunch of local roads. Because we're saying that turning, like changing streets, is slower, a path that tends to go along one street and then up another street will tend to be faster than one that zigzags through a bunch of little streets. So it will correlate to distance some, but it's not exactly distance.
Can there be like long distances but a high speed limit?
Yeah, I mean, so that's real, right? If you can get onto the 401, especially because we're modeling you can drive the speed limit, it's faster than taking a whole bunch of local roads.
So prioritize that kind of routes
Yeah.
of high speed limits.
Let's see, so D08.
Yeah, so even when like Bloor Street West and Bloor Street East are on a straight line, we still take the penalty?
Yeah, so basically if you change the street ID, which doesn't happen very often, it tends to happen, well, like Bloor Street West to Bloor Street East. It's basically you're crossing a major street, the street ID changes. Essentially, we're assuming there's a traffic light there. We're also just making things easier. Like we could force you to like compute how much the angle of deflection is and have some lookup table. But it's kind of a pain for you to write that code. It's also a pain for us to test it because we have to make sure that our tests accept any valid solution. So to keep the spec relatively simple but still pretty realistic, we're just saying if the street ID changes, take this penalty. Does that make sense? Okay, so let me go through we're doing this in a transportation graph. So that's a pretty obvious application of shortest path algorithms, but they're used in a lot of other things. So can everybody think of anything else you might use shortest path for, besides finding travel directions in a street map? I told you this algorithm's used a lot, so I can think of some applications. Can anybody else think of any other things we'd use shortest path for? So C07, actually E06, you got in first. So E06, what do you think?
Possibly FPGA routing.
Yeah, actually you do use this for FPGA routing. So my research area is CAD tools for FPGAs. We model the routing of the chip as a graph. We do shortest path searches, and we do a lot. Those graphs have hundreds of millions of nodes, and we will search for 1 million paths through them that don't overlap. That can actually take, with a really good algorithm, that could take maybe an hour. With a bad algorithm, that could take you like 20 years. Okay, so yeah, that's a good example. Any other ideas? Okay, so C07.
Delivery route?
Sorry, can you say it again?
Delivery routes?
Sorry, still couldn't hear it.
Sorry, delivery routes?
Reroutes?
No, when you're delivering, like, I don't know, packages or something.
Oh, okay, so delivery routes.
Yeah.
Yeah, so you use this for delivery routes, which is kind of building on top of the shortest path in a transportation graph. So let me show you a few other ones. Internet routing. Okay, so you say you want to talk to, I don't know, TikTok, right, before it's banned. And the way that your packets move through the internet is a shortest path algorithm has been run to figure out what routers can you talk to, and find the shortest path through this sequence of connected routers that forms the internet to get to the destination computer. Okay, so you just say, I want to go to this destination computer, and it's the job of a shortest path algorithm to figure out, well, what routers do I have to go through to get there? And we generally don't want to go through some arbitrary sequence of routers. What we want is maybe the fewest routers, so that'd be one definition of shortest path. Another one might be least congested. So maybe we'll cost a congested router as more than an uncongested router, because we're really trying to balance the traffic and get your packets there quickly. So shortest path algorithms used there. Circuit board design. So this is somewhat similar to the FPGA routing problem. Basically in circuit boards, you can model wherever you can put a piece of metal. So you divide up the whole circuit board area into a grid. And you do that, circuit boards have multiple layers. So you can't really do very complicated circuit boards if you only have one layer of metal. So they have multiple layers of metal with insulators in between. And you have vias. Vias are basically pieces of metal that connect in between layers. You can model every place you can put a piece of metal as a node. And you can model all of the pieces of metal that can connect to each other. So they're beside each other or they're right above each other, and I could put a via, as having edges between them. And now if I want to connect the output of one chip, say I'm going to put a chip there, to the input of another chip, say I want to put it there, I do a search through all those little grid points trying to find a path. And I don't do that for just one signal, I do it for every single input-output pair of my circuit board. I find all these paths and it defines how I manufacture the circuit board. We also do this in integrated circuits. So we talked about FPGA routing. You can also do them in custom integrated circuits where you're putting down whatever metal you want. It looks a lot like a circuit board. You again divide up the space, and everywhere you can put a piece of metal, those grid points become nodes. All of the grid points that can connect to each other have edges between them, except these graphs are much bigger. Circuit boards are considered low complexity compared to integrated circuits, right? So integrated circuits can have hundreds of millions of nodes, and you need really fast algorithms to do graph search through it. Social networks. So Facebook stores, all your data in one giant graph. So they put the whole world that's part of Facebook in a graph where all your friends are connected to you by edges. There are over 1 billion nodes in this graph, so it's big. And you do things like shortest path searches to find how close am I to knowing this person, right? How many degrees of separation? And algorithms build on top of that. So social networking, social marketing companies, people who make ad campaigns to go on Facebook, actually write algorithms that layer on top of shortest path algorithms to figure out who are key influencers. I should pay this person a bunch of money, and he or she should put like my brand in their video, and come up with social media ad campaigns. So those are coded as graph algorithms. They're not just shortest path, but if you get into what are they built on top of, shortest path algorithms are a key component. Okay, and there's many more besides that. So shortest path algorithms are really important. Okay, so let's just start on algorithms for this. Okay. Okay, so our first algorithm is not going to be all that good, but it's an important graph algorithm. It's called depth first search. But this is not going to be what you write for milestone 3. I just want to explain a relatively simple and useful graph algorithm called depth first search. Okay, so depth first search is written with recursion. So I need a data structure that's going to store some information about my nodes. You're going to find in all of these graph algorithms, I need to keep some scratch data, like some temporary data around for every single node. So I'm going to do that by just saying I've made a vector, because all my nodes, they're intersections, so they all have IDs. They start at 0, they go up to some number, so they're pretty convenient to put in a vector. So I'm going to make a vector of some data type called node. Whoops. Let's see if I can bring that back. Okay, so I'm going to make a vector of some data type that I've defined called node. I really don't want to do that, okay? So I've got one of these for every single intersection in my graph. And I'm giving you a little sample graph here. I want to go from source to destination. My main function just calls find path. Okay, that's going to be my main path finding algorithm. And it passes it the ID of the source node and the ID of the destination node. And it just gets a Boolean. Did I find a path or not? Okay, so now I've got to write this find path algorithm. And I'm going to write it first using depth first search, which is a recursive algorithm. It's a recursive algorithm that's very similar to what you did in a binary search tree. Okay, so the find operation you wrote in a binary search tree is very similar to depth first search in a general graph. Okay, so when I'm writing a recursive algorithm, okay, I'm starting at some node, source node, trying to get to a dest node, and the recurrence is just I'm at some node. Okay, I'll call that the current node, and I want to make progress towards my destination node. Okay, that's how this recursive algorithm works. So in recursion, I always need my base condition, my exit condition that stops the recursion. So in this case, I kind of already showed it. What do you think the thing that stops the recursion is? All I have as inputs are current ID, right? That is the node I'm at. So maybe I'm at this node, and the destination ID. So what do you think what should end the recurrence? I'm supposed to return a Boolean that says whether I found a path or not. So this is not that hard, if you remember recurrence. I need a case where I stop recursing. So what do you think? Do you have an idea? Yeah. Okay, so I'm going to put ece297 on. What is your idea?
So once it reaches the destination,
yeah, so my end condition is just, am I already at, okay, so this is like my cur ID here. Am I already at the destination? Okay, so if I'm at the destination, I found a path, I should return true. Okay, but right now, let's look at this cur ID. I'm not at the destination, so what should I do instead? I can't return false. False would mean there is no path, but I can't guarantee that yet. So what do you think I should do?
should you like obviously call the function the same function find path?
Yep.
With like an incremented current ID?
I can't just increment current ID, because maybe this current ID is 2, okay? And maybe this one is 3, and this one is 4, and this one is 5. So if I increment it, I just jump to some other part of the graph.
Yeah.
So but that's the right idea.
Oh, no. Find source.
Okay, so what I should do is I should basically look at what I can reach. I have these edges. I should look at the edges and see what can I get to in one step. So I'm basically going to look at all my outgoing edges of this node, okay, this current node. And I'm going to say, well, what's the ID? Basically, what are the IDs that I can get to? So I can get here, and I can get here. And for each of those nodes,